Hello, everybody, and welcome to the June, I can't believe it's June already, meeting of the Howard Astronomical League. We have an interesting speaker, a local speaker tonight, and I think you'll enjoy his talk and along with our regular uh, club things that we do. So I see there's somebody already in the chat. Um, okay, hello, Jamie. Um, so um, I'll go ahead and get started. So first things first, introductions, or our agenda is we'll do some introductions. We have a couple of announcements of our book of the month. Our speaker is Professor Marcel Mabson um, of Capital Technology University. And then we'll do our regular What's Out in the Sky this month and What's Up in Space. And our What's Up in Space is it's going to be like newspaper headline style. Uh, anyways, so, and then we'll do, it hasn't been a good few months for imaging, so we don't have too many images, but we'll do a couple of those. So first things first, are there any introductions? Would anybody like to say hello or introduce themselves? Any new members or in the room or online? Okay. All right. Um, that's okay. Uh, I can tell you we keep getting a lot of new members joining the club. So, which is part of why um, one of our recent events was our new member mentorship night. So, in terms of upcoming events and star parties, we have had a bad string of 3 rainouts in a row for our public star parties. Um, but I think I can feel it changing. It's gonna be good this month. So this Saturday we have our members star party. I think Wayne is hosting that. And then on July 5th, I usually write down who's going to be the host, but I forgot to do that this time. July 5th is
Someone's
our,
mic is open.
can somebody, I have a hard time. I need 2 screens here. I can't see who's who to mute them.
They appear to be muted at this point.
I am not muted. I'm looking through the list of people. It looks like everybody's on mute. I don't know. Were you getting feedback from me? Oh well, we'll just keep.
You sound okay to me.
All right, we'll keep pressing on. So, yeah, so we have a public on July 5th. I don't think we've ever had a public star party, or at least I don't remember having one on the July 4th weekend, so it'll be interesting. I don't think there'll be any that's Saturday. Friday is the 4th where all the fireworks shows. I looked online and couldn't find any lists of fireworks in our area, so we should be good to go as long as the weather holds out. Recent events, like I said, we had our members mentorship night on the 31st. The forecast was really looking good, and then it kind of was touch and go there with the clouds, but we still had about 10, um, I would say, well-seasoned HAL members show up and ready to assist. And we had about 10 new members, people with new gear and seeking like some help. So it was it was pretty much a one-on-one kind of evening. We spent a lot of time. I spent some time working on Satish on his auto aligned auto. What is that thing? The Next Star? No, not the C Star. It's the auto aligned thing for the Next Star. Um, and I know that, is anybody online that was there that had a good experience? Want to say anything about membership night? Is Jose on? Jose spent a lot of time with somebody helping them work out some kinks of their gear. Um, oh,
I was there.
did you have a good experience there?
Yeah, with the person I helped, I think learned a lot. And she's very happy that we were able to get an image in between clouds.
Great.
Even though if we weren't polar aligned, because we weren't able to polar align with the clouds.
With the clouds, okay. So yeah, I mean, I think we will try it again. Well, like I said, we have quite a few new members like that have joined in the last few months. So I think we'll do it again sometime, or offer it at least. We had a couple of impromptu star parties. Thank you to Wayne and Jose and Ernie for opening up the park. And as I've said before, you can go to the website and opt in if you're not getting the emails on the impromptu star parties. We had a sky watching event with the Howard Nature Conservancy up there on Route 99, and it also got rained out. So stand by, we're going to reschedule that. And the idea is, just to share the night skies with some of their members, get out under the stars, maybe recruit some new HAL members, um, and just kind of have a star party at their place. And so I think at least the last time I checked, the forecast looked good for this Saturday. Hopefully we'll keep our fingers crossed and that one will go well. Krystal, are you on?
Yes, I'm here. Can you guys hear me?
Yes, we can.
All right. Hello, everyone. So my name's Krystal Rolan. If you don't know me, I'm going to present the book of the month. So this month's book is a recent donation. It is Starstruck, a memoir of astrophysics and finding light in the dark by Serafina El-Badri Nance. I do put a slight disclaimer that this book, while accessible to all audience levels, may not be most appropriate for our youngest readers just because it touches on a few topics related to trauma, divorce, cancer, more mature things that may not be appropriate for maybe children under 12 or so. Otherwise, this is an incredible story. Basically, Serafina El-Badri Nance is a astrophysicist, a science communicator, and also a women's health advocate. A lot of her research actually relates to understanding how the rate of seeing large stars go supernovae allow us to better understand the expansion rate of the universe. And so this book kind of sprinkles and parallels in the science of the cosmos along with her own personal story. I particularly enjoyed this novel due to relating to a lot of the struggles that she found as being a woman in science. She shares a story about how in a summer camp, a man was invited to set up a telescope so that the kids could see the night sky through the telescope, and how she left that conversation feeling super discouraged. That the guy basically said, you know what, astrophysics is super hard. This isn't for you. You don't belong. And it broke her heart. And these stories, unfortunately, are not uncommon for a lot of women. And so I think it's a great book to give you some inspiration for those rainy days in life where you really need the perspective of just why it's so critical to communicate to young girls and to young scientists alike that science is worth pursuing despite the difficulties one might find in life. The book is incredible in the sense that she really weaves together her personal narrative with the kind of backdrop of where we're going from the beginning of the universe to our theories of how it will end. So I was really moved by this book, and it is a recent donation that will be available once I return to the country in about a week.
Oh, hey, thank you so much. I was wondering I forgot that you were on your trip and was wondering why you weren't here. You're always here in the Nature Center. So
Yes, I'm heading to London like right now. I'm like 10 minutes from Dulles. So I will be back next week
all right, good luck,
and have this
Marsh,
book available.
shepherding all those young minds.
Okay, thank you.
I
Okay,
think they're going to the Royal Observatory while they're there. That'll be an interesting experience.
okay. So without further ado, I would like to introduce Marcel Mabson, a professor of practice at the Capital Technology University right here in Maryland. He earned his BS there and has supported a number of space missions. Since joining there, he's supported Spaceflight Operations Training Center, Alpha Observatory, and various projects that support the next generation of engineers and provide mentorships to prospective and enrolled students. He's earned various awards, and I'm very excited to introduce him and have him speak here. So let me now think that's what I want to do.
Maybe you can go to slideshow.
Can't see from here. Change glasses. Can you guys see this the screen? The presentation from Capital Technology University?
Yes.
Okay, great. If I can just get my mouse to. Okay.
Thank you. Well, thank you, Victor, and thank you for the entire league for the warm invite. Looking forward to speaking today about our Alpha Observatory here at the university. If you're not familiar with Capitol is located at, if you have ever been on 295, we are on the Powder Mill Road exit. So make it right on Powder Mill Road. We're right down the street from off that main road. Capital's very unique is that we are in the middle of all major space major agencies. So we have NSA up the street, NASA Goddard Space Flight Center about 10 minutes from the road, and we have Secret Service training. So it's very common for a lot of agents to come to campus and do the training on site. So this is our Alpha Observatory. To give a little bit background on myself, I've been a professor of practice here at the university since 2014. My day job, I fly NOAA satellites for the Weather Service over here in Suitland, Maryland. And in my third job, I work here at the university for teaching. But I've always had fascinating with space. My mother could tell you that from a young age, I could tell you the names of all the space shuttles, when they had their first launch, what made each one special. And you could always find me outside on deck in 20-degree weather or 90-degree weather outside with my telescope, looking at some weird star cluster, getting bit by mosquitoes and other creatures outside. So astronomy has been a very part of my life, and having support in this Alpha Observatory on campus allows us to get back to our community. So how did Alpha come into existence? So Alpha is a very unique project for our university. Capital is almost 100 years has never had a telescope on its campus at all. Where the university sits at today is actually used to be called the old Belster Speedway. So NASCAR actually raced here on campus for 20 years, and the university took over that site back in 1980. So we've been there ever since. But Alpha came into existence from our lab managers. Because of our program, our software allows us to predict spacecraft orbits, so we can tell you where a spacecraft will be at today, a week, and a year from now. And the students have a very interesting idea. They say, well, we have all this software that we can predict satellite orbits, if they're in low Earth orbit, or on the moon, or deep space. Why can't we do the same thing to do for asteroids? And so when the idea was initially pitched to us, we said, yeah, this could work, but you guys need to do your system engineering first to prove to us that, yes, the telescope in our facility can work. And so a year of work went by, and they convinced us to submit a proposal to the Maryland Spacecraft Consortium, and they actually approved our proposal back in the fall of 2021. It wasn't until the summer of 22 where the observatory came on campus and construction began. But for Alpha, it was more important for us to not just observe the night sky, but to use our unique programs on campus to automate the entire function. So for Alpha, some of the main goals we had was to automate our entire observation run, from the planning to the observing to the processing of the images to detecting of the asteroids. To do all this, have a pipeline where from start to finish, it's all done hands off and can run by itself. The telescope is also configured to do variable star studies, so we can look at variable stars and exoplanet transits. And when we have free time, we have what's called the Night with Alpha program. And this is what we have once a month. We have a live stream event through our university YouTube account, where we invite community members and interested students to come to campus or come to a live stream event to see how Alpha works, how we do image processing, how we find asteroids and comets, and get them engaged into STEM. It's a good way to get them involved. Funny story about Alpha, where Alpha is located at behind these trees is actually is a small community of houses. It's not too uncommon, especially when we are opening the dome for the very first time at nighttime, to see small children walking around the dome, sitting on our deck here, waiting for the telescope to come at them. Because they've seen it from their porch, they want to see what the noise is all about. So it's on the telescope here. So why do we care about asteroids? You know, we get this question a lot when we have students that come to campus for the first time, and they see this small little white dome in the middle of the field. Why do we care? Well, I always tell them that you don't see any dinosaurs at McDonald's, and you don't see any. You might see the cousins, but you don't see any big dinosaurs roaming around anywhere. That's why we care. The dinosaurs were wiped out by a comet that crashed in the Gulf of Mexico, and so if we don't want to go out like the dinosaurs, we better keep an eye on some of these asteroids. And what asteroids are is that they are nothing more than leftover fragments from the formation of our solar system. Made up of iron, ice, and a combination of all together. But the majority of these asteroids are pretty much in stable orbits. We can thank Jupiter for that. They form they form around the asteroid belt between Mars and Jupiter's orbits. And Jupiter does a very good job of doing planetary defense for us. It shepherds all the major asteroids, about 80% of them, either in the asteroid belt or the Trojan asteroids that live either ahead or behind Jupiter's orbit. But there are some that we call Apollo asteroids that come within Earth's orbit, and these are the ones that we want to look at and monitor. Okay, okay, to do it. Think about lost it.
My computer do.
Disable. Go down slide.
Oh boy. This is a one.
There we go.
Okay, the mouse just drifted.
So thank you for that. Appreciate it. So this is a quick little visual of why we care. One day I had my intern take an image of a random spot in the sky. I said, take a 30-second image anywhere you want, don't care, take an image of it. And this is a 30-second image of Alpha's field of view, and we can overlay all the asteroids that are in this field of view. Our field of view is about 1.5 times a full moon. So our field of view is quite large. In this image alone, there are 108 asteroids in one field of view. The Minor Planet Center, which is supported by NASA, they keep a catalog of all the asteroids that we ever cataloged. Right now, there are about 1.4 million asteroids in comets cataloged right now. And some of them are pretty much harmless. But the ones we care about is this one example here. These near-Earth asteroids that come within Earth's orbit have what we call high inclination orbits, meaning that if you look at the planet in the solar system, they are very high up, between 60 and 70 degrees inclination. What makes them a problem is that most of these asteroids are small and they can hide behind the sun's glare. If you ever try to look at a new comet, for example, most of the time when you see them is either in dawn or dusk time. These asteroids are the same exact thing. And so most of the time we find a new asteroid, and especially if it has a close flyby, we have already missed it. So for example, a couple of years ago, asteroid 2020 B4, this was a pretty size asteroid. It's about the size of a small beetle. Came within 40,000 kilometers of Earth's surface. The problem with this asteroid is that we only found this thing 15 hours before it came by to us. If this was larger, we would have a problem. In 2 years from now, we'll have asteroid Apophis will be coming by as well, and it will come closer. This asteroid will come within the geobelt of our satellites. Originally, Apophis was a potential threat because this asteroid will start to impact the Earth, but as we define the orbit, it's going to pass within that orbital belt. This is why we want to look after some of these asteroids. They pose a threat to us. We want to see where they are. Yes, sir.
You were about to talk about what telescope you had in the.
Yep, I will next slide. Yep. Okay. So how do we observe this comet? So what's the best way to observe these asteroids? Best way to do it And so look at that sky and look at it consistently. You can see here in the image my daughter Grace here out with me one night doing just that. Taking our telescope and looking at that sky. But there's a problem. These asteroids, because there are so many of them, they need to be looked at over and over again. But if you ask astronomers, they also want to have their own studies too. Some are interested in planets and black holes or other objects, and the amount of professional observatories are not high enough that where astronomers can have that can have time. So, for example, James Webb Space Telescope right now it has 104% uses right now because everyone wants to get on board. So there's not enough telescopes to do this work. So most of the time you have University of Hawaii has 2 telescopes, Pan-STARRS and Atlas, Low Observatory, and these guys primarily do most of the work of finding asteroids. The new telescope called Vera Rubin Observatory in Chile will be coming online this year with the goal of it will observe the night sky every 3 days with the world's largest CCD camera. And so it will detect about 95% of any new asteroid that we might detect, which is pretty nice for us to have. But just like Vera Rubin Universal telescopes, the problem is follow-up studies. Yes, you might find a new asteroid, but the initial orbit is not valid enough for us. And so that falls on the small universities and the amateur astronomer now to do these follow-up studies. Yes.
This is probably a very obvious answer, but this is Vera Rubin observatories in the southern sky.
Yeah.
So we're not going to catch anything in the northern sky.
That's
right?
correct. Yeah, okay. That's correct. There is talk of University of Hawaii. Their Atlas telescope they have on the Hawaiian Islands, in Chile as well, and in South Africa. So they pretty much get north and south hemispheres. Their goal is to at least have 72-hour notice. They've never had test that yet of a new asteroid impact because. But Vera Rubin at least will get all of them in the southern hemisphere. There is talk if the on the Hawaiian Islands, a new telescope will come online about the same size as Vera Rubin, but because of protests, that will probably get delayed until it gets constructed. But yeah, that's the problem. So some asteroids are in the southern hemisphere and they're not seen to us. We have to keep up with them. Good question. Yeah. So this is Alpha. So Alpha is located here in Lower Maryland, and Alpha itself is a medium class telescope, which is why Alpha is called a large. At least for us, it's a large telescope. Alpha is a C11 SET telescope mounted on a Celestial CJX mount in a next dome observatory kit. One thing that the students wanted to do when we first used Alpha is because these asteroids can move relatively quick, between 1 and 4 degrees per day, we need to be at a fast F ratio. So Alpha operates at an F2 F ratio about 95% of the time. We do have the capability to swap and run at F6.5 with filter mirrors and filters, but primarily Alpha stays in this configuration most of the time. We have a weather station at the site, so we can see local weather conditions, if it's getting too hot. And most important to us, we have a outdoor 5G network. This is a cellular network that we have that's independent of the university network. So this allows us to have access to the telescope anywhere in the world. I had one intern that was on vacation in London. She was able to come into the Alpha, run her session, just as she was doing here she was here on campus. Alpha sits in a high Bortle scale. We are at about Bortle 6.5 right now. So not in the white zone yet, but it could be worse. But Alpha sits inside this spot here. I put this here because we have a little model on campus called Find a Way or Make a Way. And if you ask our students, just like the professors, we are very stubborn. We hate being told, no, you can't do something. No, you can't do something because of technical reasons. No, you can't do something if you don't have enough money to do it. Instead, we challenge our students to make the impossible possible. Figure out a way. Yes, you might be in a high Bortle scale. yes, you might be limited to more brighter objects, but what can we do technology-wise to help us find these more fainter objects? Is what Alpha does on a regular basis. This is Alpha's first intern, Juliana Bruce. So she actually constructed Alpha with me during the summer of 22. I will say this next observatory was a pain in the butt to put together. We probably took this thing apart 5 or 6 times before we got it all straight. The shutter motors themselves, we took about a year before we finally can open and close smoothly enough. So it was quite a hassle.
We have the same issue with our Humpy Dumpy.
Yep. So
shutter motors are always scary.
Yep. And I won't lie, for us as professors, when they are opening up the dome for the very first time, I always peek inside remotely just to make sure we had any issues. Because it has actually locked up before midway up the shutterware. We're like, can't do anything about this today. But for what it does, Alpha works. When it works perfectly, it's happy. So Alpha commits a 20-day commission activity. And one of the things that we were concerned with Alpha initially was because we were operating at F2, the focus point of the telescope can be very small. So one of the things we wanted to make sure is that the telescope can be focused properly over and over again at different temperature settings. We were also concerned about our collimation. Alpha uses the Hyperstar system by Starzona. And at F2, the collimation can be very tricky at F2. So it took us about 4 or 5 nights to get collimation just right for the telescope, so we didn't have any egg-shaped stars on the scope. This also allowed us to test out our tracking of the scope and run a lot of our automated signals for the very first time. Alpha was quite lucky when it came online the first time, because when it came online, we had 2 bright comets that came by, Comet Atlas C2, and the first ever comet that came by. As we were able to track those objects, and we actually received our Minor Planet Center code in about 10 days after we started commissioning activity. So it's pretty fast for us to run. But you can see how wide Alpha's field of view is. You can see a full moon. This is actually a crop version of our moon picture. And this here is the M13 cluster, or the M13 globular cluster. I always note this to the students because they always ask, well, how good are your optics? Well, if we look at the cluster all the way on the left side here, there's a small little galaxy right there. If you were looking at that through a regular telescope at f6.5, you're not going to see it unless you're exposed for 15 hours. That image is only an hour and a half exposure time. So it does a good job of capturing light. This here is,
What was an MPC code, that third?
Sure. MPC is the Minor Planet Center. And so this allows us to submit tracking data of asteroids to their catalog. Okay. So we are tracking an object and we update its ephemeris. We can submit data to them. So we observed Atlas. So right now we observed over 400 asteroids to date. And so they capture all of our tracking data from that.
New asteroids, 400 new ones?
No, there's 400 in general.
Okay.
There is a story in Alpha that even though we can't claim it, we did find our first asteroid that no one has discovered yet. But University of Hawaii got to it first.
No.
So we always give them the fingers because we're like, we're so close. We actually caught that. They actually caught it 5 minutes before we did. So we were so 5 minutes before we did. And the rule is for Minor Planet Center is whoever cataloged it first. So they had to get to it first. My intern, and I'll get back to the presentation in a second. So my interns do all the work for the process. And so on this day, she gave me a call, practically screaming, "Professor, I think we found it. I've double checked. It's not a satellite. It's not space junk. It's an actual satellite. It's an actual asteroid. I think we got it." She had already picked out a name for it and everything. Had an email typed up for her mom, and then you got the email back, "Look, you can have it." So we're trying, but to get that is very hard to pick out to get anyone. But we've observed 400 asteroids to date. Yes, sir.
Tell us about that asteroid.
Yeah, so this was asteroid 2022 A2. So this was a high inclination asteroid. And she actually found it by mistake. So the automated system that we have will pick up false readings sometimes. And so she just happened to go back because we have a rule, if you get false detection, you have to manually go back and reprocess the image to make sure it's not noise or nothing like that. And so during her process, she's like, no, I think this is a real object. And we had actually caught it 2 nights before before it got captured anyway. And so she went back 2 nights ago and said, yep, this is actually a real asteroid. So it was fun for her to do that.
Is it a little guy?
Oh, so the size was about. Size is difficult for us to measure for the asteroid size because we had to look at their light curve and their spectrum. But it was small. It's about the size of a beetle to a Greyhound bus. So they can't quite. So it's in the middle of that size. So it's quite small for asteroids. Yeah, she found it. So even though it was claimed by Hawaii, Astro claimed to us, hey, you found at least one. Don't care what you right. Hawaii said. But there are some challenges with operating a remote observatory. To start Alpha, when we run Alpha, there is no one sitting in the dome. It's all remotely controlled. And the first year we had Alpha, we burnt through 8 outdoor people. We burnt through 6 PCs, mainly in the summertime. This dome is not thermally controlled. So if it's 100 degrees outside, we're 105, 110 degrees inside the dome. So we are baking inside the dome. So actually this year we went ahead and we purchased a outdoor rated PC that can go all the way down to 15 degrees and go to 100. It can go all the way to 116 degrees in temperature. So if we burned you that one, I'm gonna not be a happy professor for that. Another issue we had too is because we're remote, the observatory has to be able to save itself if we detect a bad weather condition approaches. So if we're operating, we're doing slews, if, for example, a cloud cover comes on board or it starts to rain, the dome is smart enough that it will stop itself, close the shutter, park the telescope, wait for this to clear up, and then pick back up where it started from again. This has stayed Alpha. I can't tell you how many times this has happened. A student has run Alpha in the middle of the night. Even if the forecast is perfectly clear, a rain comes over, it stops, and continues on its merry way. We need to be able to power cycle. We can power cycle about 90% of the dome remotely. The only thing we can't power cycle is the mount itself. Celestron does not give you a nice way of resetting the mount remotely. So if there is a power issue at the dome, it is a manual, have to restart the mount. But everything else we can control from home. One thing I get a question about is how do you get data off of Alpha? Even though we have a high-speed router at the dome, it takes too long to transfer data off of Alpha back to campus. Each night we generate about 100 gig of data per session. So it's actually easier for our students to take a expandable drive, walk into the dome, plug it in, wait an hour, and then get it back. So that's how we get data off from the dome. And you see here various slew tests here on the top right-hand corner here. You can see one of our tests where we actually move the dome back and forth, and our shutter test. Yes.
Out of curiosity, what do you guys use to do your remote power cycling?
So we have a Wi-Fi switch inside the dome. Mm-hmm. So we have everything that's that switch, and then we can remotely control that switch from anywhere. And so we have each port labeled, so we can recycle the computer or any part of the dome. We can send command to recycle it. There is a backup UPS unit inside the dome as well, so we can also go do it through the UPS unit as well. That UPS unit is usually our fail-safe. So if we do lose power, we have about 10 minutes of power from that UPS unit. So if that triggers, it will automatically save itself and power it down.
Yeah, I do a lot of work with digital signage as my day job. And like we do a lot of the same kind of like remote controls kind of stuff. So I was just curious.
Yeah, that'll be used. Yeah. Yeah, there we go. So how do we automate Alpha? So we use a program called Prism. And on the market, there's plenty of software packages that can do automation. Some more expensive than others. But Prism does all of our automated activities for Alpha. It can do dome control. It can rotate the dome, rotate the dome, open the shutter. It can do plate solving. So when we do a salute to a target, a plate solving team will run and will make sure our target is in the center of the field, no matter where we're pointing at. In our salute. It also does our camera control. Alpha uses ZWO cameras. We have a 1600 mm as our main imager and a 1290 mini as our guider. And so Prism takes care of all of that management for us. But most of all, when we do a plan activity, it runs our planning routine as well. So it will we will plan set of targets, and then we'll optimize when we can make a slew to that target. So it works from the first is going to set first and works its way west as it goes on. And you see this quick example of what Alpha was doing 1% of the night. So you can see our tracking data here on the right-hand side here, our temperature setting for the cameras and our focus routine. So we can automate the entire routine in Prism. We can push a button, it will run through, and then at the end of the night we have nice pictures at the end of the night about. Yes.
Do you use filters, or you're interested in the monochrome?
We do have filters. So Alpha has F2 optimized narrowband filters, and we have RGB filters. When we are doing asteroid studies, we're typically running the green filter most of the time because that's a nice standard filter for photometry that we're going to use. So that's what we use for that change. Filter changes are manual because we're operating at F2 with the Hyperstar system. We have a filter draw that we go outside, we flip over, and we change it manually. So that part's manual. And as soon as I can do it anyway, so it's fun. So how do we do our asteroid plan? So the first thing we do is, since the Matter Planet Center holds all of the asteroids, all 1.5 million of them, it contains all of the ephemeris data for the asteroids. And what ephemeris data is location data for us to point to say, at this location at this time, you will find your asteroid target. So what students would do is we would typically go to Matter Planet Center first, look up any new objects that are doing close approaches. So anything that's coming by. Why go for those first? Is because we want to refine their orbit. Most of these objects have only been discovered for a few days, so we won't go after those first. Then we start going through comets. For the comets, we're looking for things that are going in outbursts. So most of the time when we do comet hunting, all we care about is this comet active or is it quiet? If it's active, we'll go back to it the next couple of nights and kind of monitor it from there. And then we start cutting data for our asteroids. Yes.
Can you explain quiet as active?
Sure. So as a comet comes towards the inner solar system, all of that ice gets heated from the sun.
Right.
And so now you start seeing the tail will start to come off.
Sure.
As it comes back around again, the ice starts to reform solid again, and you lose that tail. So what we're doing is, for looking at these comets, is seeing, is it active or is it quiet? Because when these comets are quiet, they're so far away and so dim, you can't really see them very, very well. But when they're active, they create a natural halo around them, so now you can see it better from all points of view. So that's kind of what we mean by active and quiet, for the most part. And then what we started doing, and we started setting up targets. Now, one thing that Alpha can't do is, unlike the Vera Rubin telescope, we cannot observe the sky in one go. So instead, what Alpha does, we create what are called sectors. So the students will go ahead and pick a sector per night and say, we're going to observe these sectors tonight. And what we typically do is we will observe at different declinations. Sometimes we'll be at 60 degrees, sometimes we'll be right around the ecliptic. And we'll pick these sectors throughout the nights. And as we run, we move the sectors night to night. And so I started with something like this. So this sector is in the Leo constellation here. And what we've done as we said, in this sector, we're going to observe these asteroid targets. Now, what I have selected here, you might think, oh, well, that's just one target. But when Alpha looks at the target, you're just not looking at one target. There are some situations where we might look at a target and we'll get 10 objects from it. And so each time we look, we'll pick up more and more asteroid comets, more asteroids as we go through. These are all planned out in PRISM. And one thing that we have to be cautious about when we are doing these asteroid studies is how fast the object is moving. We don't want to see a star trail from an asteroid. So we don't want to see a trail from the asteroid. Instead, we want to see a nice, crisp, round star in the image. Reason for that is because the software that does our prediction might think that's a satellite and not an actual asteroid. So what we do then is based on how fast the asteroid is moving dictates how long we can expose for. Normally, alpha exposes between 30 and 45 seconds. That's more than long enough for us to get enough signal for our first target. So once we have our asteroids, we then produce a image file like this on the left-hand side, which has all the image sequences that we're going to run. So it tells things like location, number of images we're going to run. Do you want to autofocus or auto guide during the sequence? And it will start running off the sequence. Now, at PRISM, there are some situations where if I run it like this here, the software will automatically pick when the targets will be executed. Some might happen. So, for example, when we do our sectors, they're set to run all night. So some objects will be visible, say from 8 to 12, and some will be visible from 1 to 5. So the software will pick the ones that happen early versus late. But there are some situations where, say, for example, like right now we're looking at the Nova and Columbars. That's supposed to start any day now. We have a hard-coded look at this object first, look at this object in the beginning, middle, and end of the session. We hope that this thing will blow up and we can catch it. But it's on its own. But basically, you put these little checks in the plan sequence. So if anything comes up, if anything that is a turn of opportunity, we can see and monitor as we're going on the session. So when Alpha starts running, this is a quick picture of Alpha getting ready to start a sequence. One of the biggest points for Alpha to do every single night is we capture calibration frames every single night. So we have what I call a dark library, and this is just a set of images that tell us how much noise is in the camera. And what we do every time we start, we create what's called a flat field frame of our mirror. Basically, for anything that has dust on the mirror to take them out of our images. When we start, Alpha will automatically slew up 7 degrees up and get a nice flat field of the morning sky. The software is smart enough that if it sees a plane to come through or a cloud, it will wait a few minutes and then try it again. If for whatever reason calibration fails at start, it will wait and do another one at dawn time that's before it closes again. But once the sequence starts, PRISM is in control of all the execution sequences of Alpha. So for example, every hour, the system will stop. It will refocus on a new target. Or for single target, it will do a refocus routine on that target. We have a horizon model. So the team actually went ahead and looked at our entire surrounding, modeled where all the trees are at, all the buildings, and it will not take an image if it hits that horizon spot. So you'll never get a situation where you come back next day and you got trees in your image. Alpha doesn't get it. What's also nice about Alpha is it will always slew between targets. So all those targets I had planned before, it will go through, run through all those 20 objects, all hands off. Students can monitor the runs by their phones. Alpha will send out little alerts to say, hey, I'm on this target right now, this is what I'm doing, and we'll continue on. On average, Alpha will monitor between 20 and 40 objects per night. And we will collect about 1,500 images per night. You're probably gonna ask why we cut so many images. I'll get to that in one second. And our cabin temperature is about -15 to -25 ambient temperature. In the summertime, we will probably be at that lower point of 15 degrees minus temperature. But in the winter time, we are nice and cold. We've seen it down to minus -35 at some point. But it really does a good job at that point. But let me go back to the 1500 image and why we do that first. Remember because alpha is in a high boredom zone, that background noise is going to be our enemy. So the only way to extract out the data from our asteroids is to take lots of images. So to get a higher signal ratio, you want to get all data you can. That's why alpha creates more images. So every time we do an asteroid, we will take between 50 to 60 images per target, typically. That's why we have so many. So this is an example of our image processing that we do with the asteroids. So this is a quick 30-second image of asteroid Ontario that we took last year. And what we do after we get all our data back is we start post-processing. And our goal is to take out as much of that background noise as we can from our images. So the very first thing we want to do is we will sort the images by their quality. Is there a cloud in the way? Did we have bad focus routines during the run? Those will automatically get taken out first. If we had a bad pointing for whatever reason, if our asteroid is not in this field of view, we take them out. So it does all that first. So by the time before we even do anything further from this point, we have a nice clear set of images to work with. And now we're going to start to see our processing. So the very first thing we're going to do is we're going to do calibration. So we're going to add our darks and our flats to clear up noise from the camera. And then we're going to go ahead and remove the background gradients as much as we can. We can't do a whole lot with the gradients sometimes, but we'll remove the background gradients. And our goal is to start cleaning up the image as we get further on down the train. And by the time we get to the end, we do our noise reduction. It's a simple Meridian 3x3 filter that we run, and it cleans up about 80% of the noise that's in the image that we have. But another trick that we do is, at least for us before we go any further, is we want to see if the asteroid is actually in our image. So what we'll do is we'll create what's called a movable stack. In astrophotography, typically you're just stacking image one after the other in one spot, right? The same thing over and over again. But with a movable image, what you're doing is you are telling the stacker, hey, this is the movement of my asteroid. Any movement of the asteroid, I want you to ignore. So all you're doing is stacking the asteroid itself. So depending on how, if the asteroid is moving fast, you actually see star treks. But in Ontario's example, it's moving quite slow, about 0.28 arc minutes. It was very slow. But if you notice at the very top, where I have my little red circle at, that's our asteroid. So I've gone from that, where you can barely see it, to now that. So now I know my asteroid is here. But how do I know that's an actual asteroid and not a star? So we go back to our good friend Pluto, before it was unceremoniously demoted as a dwarf planet. The way we look at asteroids is we will blink them together. So things like galaxies and stars, because of their distance, they don't move. But things that are in the foreground, like asteroids and comets, will move across the night sky. And so what we'll do is we'll blink the images together to see if anything moves. So in these two examples here, of asteroid 1999 K5 and asteroid Cacus, these are asteroids, you can tell they're moving because they're asteroids. One quick thing you probably notice, if you look at Cacus on the left-hand side here, those four little trails you see, and this is the kind of power about alpha, those four trails you see are satellites. When we took this image, Starlink had just deployed the Starlink satellites, and they happened to come in off the review, which is annoying. But that's how we know they have asteroids. But now here comes the fun part. So we take our data that survived our post-processing thing, and we put this through a commercial utility called Tycho. Tycho is a asteroid detection software that will automatically detect asteroids by using what's called a synthetic track. I'll go back to why we have so many images. So remember, stacking is our friend because we can increase our signal of our asteroid. What Tycho can do is if I have a set of 60 images now, I can tell Tycho, hey, every subset, I want you to create a stack of X number of images. So now each stack that I have, I'm guaranteed I have a good signal-to-noise ratio to avoid any false detection. So what Tycho can do is it will scan through the entire field of view and look for anything that moves. If it sees something that moves, it will match it against the NPC database, match it to a known coordinate, and create what's called a Minor Planet 1992 report. That report sends out to Minor Planet Center that tells it where the asteroid is located at, what the speed of the asteroid was, and what was the magnitude of the object. Depending on how many asteroids we're trying to observe in a given target, this process takes between 1 to 3 hours to run per target. So it takes us about a day to run through the entire set of asteroids that we're using for Alpha. So it's a little while to run. That's why we typically will do this stacking first to see the asteroids in there first. Because if it's not, we probably will just ignore that asteroid. This little map you see on the right-hand side here is so Tycho will give you a map of all the objects that you have observed. So this is from one night of Alpha running. So you can see that the majority of objects that we find are along the ecliptic, but there are some that are very high in definition. The first you see on top here. Those are the ones that we're after. One cool thing that Alpha does as well is we want to plot these asteroid orbits. So what we do is the same software that we use to track satellites. This is called Free Flyer. We can predict their orbits. So this is the asteroid Daphne that we observed last year, and we observed Daphne for about 15 nights, and we were able to observe its orbit and calculate here in Free Flyer. And we're within 0.125 miles of what NPC has in their official catalog. So we are pretty much accurate versus my predecessor. What's also cool about Alpha is that we can actually do rotation studies on asteroids. And so we're curious for fast rotators, how fast they are spinning and if they're consistent or not. So this asteroid Skip that we observed in 2023, and we observed it had a rotational period of about 1.5 hours. When we reached out to Minor Planet Center, it had a rotation period of 1.2 hours. So we were able to update its rotation period from Alpha. Oh, and one more thing here, because Asteroid Apophis is coming over in 2 years' time, we're using the same exact software now to start planning our observation period for Apophis, to figure out how long we can observe it for, and what's going to be our view periods for Apophis. And this is just a quick little summary of our latest campaign from last year. Alpha ran 60 times last year, which is pretty average for our runtime. We collected over 4,500 images. We observed 120 asteroids, 3 comets, 2 exoplanets, 6 spacecrafts, and we had 98% remote availability to the observatory, which is quite good for a little remote observatory at the capital for us. So when we're not observing asteroids, Alpha looks at secondary targets. So these are our these are our variable stars like Cepheus and Eclipse variables, and exoplanets and spacecraft that come by us. So the first one top is exoplanet XO2NB in the constellation Lynx. The young lady you see on the left-hand side, that's my second intern for Alpha. And the picture you see here is her first time seeing the exoplanet transit. And so Alpha looks at these objects very often because we want to see if their transit depths change. Sometimes they change year after year sometimes, so we want to monitor that change. And we also monitor variable stars creating black curves for us as well. one that's very near and dear to our heart with Alpha is we also have our Night with Alpha program. And for these programs, we will invite our community members. For example, the lunar eclipse we had last year, we hosted a live stream event for that. So we had our 5 community members come on live stream for that. Saw the lunar eclipse from campus. But we also invite them to submit targets of interest. So if they say, hey, I've never seen the Orion Nebula before, we will actually run your sequence and we'll let them come to the lab and see Orion for the very first time on their screen. The wisdom there is actually a fun little story. One little boy in our community loves space. He loves Alpha. And one day he came by and he said, I have a science project. I want to do it on this picture. And we asked, well, do you know what this picture is? So we explained to him what this picture was and talked about how we're going to get it. And he actually made his science project from the wisdom. So he used one there for that project there. So it's our way of giving back to the community. And last thing is talk about Alpha 2. So one of the issues that we have with Alpha right now is, yes, our voter zone is terrible, but we don't run enough. For the course of a year, Alpha may run 100 times a year, and that's being generous. Typically, clouds, smoke from wildfires get in our way, and the sky conditions are just terrible. So one of the things we're looking forward to do right now is we're thinking about creating an Alpha 2 and putting this at a remote sky location. So a remote site. Prices have come down nicely enough that it actually makes it more feasible for a small university to do this. One of the things that's going to be different for us is we're changing our mounts. So instead of having a Celestial CGX mount, we're going to use what's called a direct drive friction mount that will enable us to slew at a maximum of 20 degrees a second. So instead of being limited to 40 degrees a second, we can go on to 20 degrees. This allows us to track satellites, and we can go back and forth between asteroid targets a lot quicker. With our current setup, to go between asteroid targets takes us about a minute. With this new setup, we'll be able to do it in under 25 seconds each time we're wanting to slew. Alpha will keep the same OTA. The only difference is we might go ahead and splurge and get a plane wave CDK for the inch telescope. But at least initially we'll keep the same OTA too. But the one that we like very much is that between the 2 sites that we're considering right now, one is in Texas and one is in New Mexico, is their number of days that they have on Sky. 220 for South Texas and almost 300 in New Mexico. And so we're thinking about creating an Alpha 2 to allow us to have more flexibility with the telescope. So I want to thank you guys all for your time this evening and inviting us to talk about Alpha to your league here, and look for any questions you guys may have. Any questions on the phone or in the audience I can answer? Yes, sir.
Ultimately, you're observing tons of asteroids. Is your goal to teach the students about astronomy and how to do stuff, or is your goal to find new asteroids, or is your goal to refine or do?
No, so we teach. So the university has a small astronomy club on campus, and so they're the ones that's in charge of creating our images and doing all of our planning. We teach them about hunting for asteroids because when they get into their career, they'll be doing system engineering. They gotta learn about planning activities. Things are gonna go wrong, and so we teach them about how to problem solve. And so it pretty much gets them ready for their career outside of the university. Cool. So kind of keeps them well-rounded. It's fun for me because I get to play in the field, but teach them at the same time too.
Awesome.
I have a question.
Yes, sir.
Any of your students gamers? Because I played around with Tycho once, and it seemed like it worked with GPUs. So maybe one of your students.
So funny enough, we do not use GPUs on Tycho at all. We have high-end servers that we run using the CPU. It does take longer, but it allows us to run in cluster mode. especially have full servers running at the same time. We run Tycho, and we spend on that way a little bit. So that's how we get around that. Pretty neat though. Pretty neat. Yes, sir.
One more thing. Do you know that Howard Community College has an astronomy program where they're studying exoplanets?
Mm-hmm. Yeah.
You should know.
Mm-hmm.
Okay.
Yeah, there's a lot of them that do it. Howard does it, University of Maryland does it, Gettysburg. Most of the major colleges will do it as well. The big problem is that you need to be able to observe it, routinely, right. Especially for new discoveries. Alpha does look at new discovery for actually to come from the spacecraft tests. So we will get notifications say, hey, a new exoplanet has been discovered. Can you go look at it? But because of power conditions, we miss it typically. So typically, most of the time, we're looking at exoplanets. We better have nothing else to do for a little bit. So we're going to look at it for as much as we can. Thank you. Hey, anyone else? I think this is very fun.
I have a question.
Yes, sir.
Yeah, do you allow for public observations there on the campus, or is your observations only for students?
No, so our Net with Alpha program, we allow you to, when we live stream out, when we do our live stream, we invite members to come and view our live streams. The university sends out on our Facebook page, they usually send out an announcement to say when an upcoming task is coming up. But we also do allow you, if you want to submit targets, we allow you to submit targets to us. And we'll give you the raw data if you want to process it yourself, or if you want to come to campus in the lab and see Alpha run in real time.
And that night with Alpha, you said was once a month?
Yep, we try our best to do once a month. We do, because of the weather, we do provide very short notice. We'll probably do it 2 days in advance typically. We've tried doing a week in advance, but we decided to say this is better to do 2 days in advance, and we'll just get who we get. Anyone else online have any other questions that we can ask? And feel free, because we're so local, if you guys want to come down and see the telescope one day, or we can let you know something. We definitely let you know. We have another session. We can let you guys see that and invite you guys down to come see it.
I'm sorry if you said this. I either was didn't catch it. What is it that you teach?
So I teach astronautical engineering. So this is the study of operating spacecraft in orbit. So we teach them systems engineering, spacecraft development, testing, launch, really prepares them to operate in the spacecraft field. So a lot of our students work on Space Force, DoD missions, NASA Goddard, so all of the tests.
So you're near and dear to our hearts, I think, because we all have day jobs and we all come out at night and spend all this time and energy. You've got a lot of energy doing this as your main job. So that's terrific.
Mm-hmm.
So for those in the room, Marcel brought a bunch of swag and some stuff in the background, in the back of the room there, if anybody wants to grab some materials. And for those online, I'll take some of those to the observatory with me if anybody wants to read more about the Alpha Observatory. So
great.
Yeah, thank you. Was that a question online? Well, we might have a bit of time at the end of the meeting, so if you have any other questions, Marcel will be here. So once again, thank you so much.
Thank you so much. Thank you.
Yeah, thanks, Marcel.
Yeah, thank you.
Is everybody seeing the agenda screen online?
Yes.
Yeah, I can see it.
Okay, great, thanks. So next, we'll move on to our regular stuff. I'm so glad that Jim is able to make it. I know he's coming in and out, traveling. So go ahead and take it away, Jim.
Sure. Okay, so the highlights for this month in the solar system. Mercury is actually having a fairly good evening appearance. You can catch it next week if you have a clear western horizon, which of course lately clear weather has been at a premium. June the 26th, it's going to be its greatest elevation, which also coincides with the crescent moon hanging next to it, only about 3.5 degrees away. So if it happens to be clear the evening of the 26th, it might be worth going out to a clear western horizon to see if you can catch Mercury and the moon. Next.
And clear western horizon is what's available to us at the Howard Nature Conservancy.
Right.
So being able to use their their facilities is part of why we like to have our collaborations with them and go out and do the star parties with them. I'm sorry, Jim, go ahead.
Yeah, go ahead, click. So Venus in the morning sky, unfortunately, it isn't gaining a lot of altitude. It's like the harvest moon effect, but you can still get up and see it. It's now in its past half phase, getting smaller and into a gibbous phase. Next. Mars, which is really tiny now, smaller than Mercury, actually. It's moving through Leo, though, which is kind of cool because if you catch it one night and go out maybe 3 or 4 nights later, you'll definitely see that it is buzzing along the zodiac there. Next. Jupiter is a no-go, lost with solar conjunction this month. And the next one, Saturn is pretty much the star of the show here. It's getting well placed in the morning sky if you get up early. The rings are slowly opening. Saturn went through its ring crossing period in May. Most eyepieces, when I got up and looked at it the other week, it's kind of fascinating. It looks like a ball, like a tennis ball maybe, with a knitting needle pierced through it, because you can't quite, unless you're putting some really good magnification on it, you can't quite see the space between the globe and the rings. So it kind of gives you this impression of a spike driven through a ball. It's really kind of cool. If you happen to get up early for some observing, definitely check out Saturn. And next.
It's going to be a couple of months before it's an evening object for us non-morning people.
Yes.
You think it'll still be like that in a couple of months?
It's interesting, and that's going to be the topic for next July, for the next meetings, Shallow Skies, how the rings are going to change over the next 6 months.
Okay.
So actually they're going to open up a little bit, but then they'll close again. So yeah, September, I think, is the opposition month this year.
Okay, cool.
And so continuing on with our Saturn theme here, this is your last call for Titan shadow transits. So many of us have seen the shadow transits on Jupiter, and those happen pretty regularly. I mean, almost at least 2 or 3 times a week, you can go out and catch one of Jupiter's moons cutting in front of the planet. But for Saturn, it's got a axial tilt, not too far off Earth. It's like 26 degrees. So the thing is, the plane of the orbit of the moons has to kind of align, cut across the equator. And that only happens when Saturn reaches one of its equinoxes, which, like I said, just happened in May. Click again. Okay, so yeah, so when it's at its equinox. And so right now, we're having situations like you can see here in this picture that somebody sent into the Alpo, where Titan, because of the angle, is actually appearing above the planet, but its shadow is being cast down on the planet. It's all kind of like geometry. And this is going to be your last chance for, 13 or more years, maybe. So the times are listed here. You can always go to the Alpo website. We will have it listed on our calendar of events. But this should be visible if you have like at least a 4.5 inch, maybe a 6 inch telescope. The contrast here should be fairly decent. So in a moment of fairly good seeing, you should be able to pick out that little dot there on the planet. And you can say you're one of the few people that has seen a Titan moon shadow transit on the ringed planet. And I think that's about it for this month.
Cool. Thank you so much. That was really cool.
You're welcome.
You said Alpo website, and my brain, we've heard Alpha all night. I thought it said Alpha website. Okay, Wayne.
Okay, so as Victor said earlier, we're trying a different format this week or this month. Instead of making a deep dive into a single paper, I'm going to give you kind of headline information on a number of topics. So our first story tonight, in the sense of newspaper, our first story tonight concerns JWST observations of aurora in Jupiter's atmosphere. The observations, as you can see on the image at right, which is the left-hand image is the NIRCam JWST image, and the right-hand image is an ultraviolet image from the Hubble Space Telescope taken at the same time. So the observations were made using NIRCam on JWST at a wavelength of 3.36 microns, which includes emission due to the trihydrogen cation H3+. So it's a 3 hydrogen molecule that's only got 2 electrons in it that are holding all the 3 atoms together. The observations revealed that the trihydrogen cation emission is more variable than previous believed and appears to have a lifetime of about 150 seconds. These observations more generally present a diagnostic window for the Jovian magnetosphere and ionosphere. So, and there's a link at the bottom that you can get off our YouTube video when it gets posted if you want to go get more information, or just look for Jupiter's auroras. You'll probably find it. So
I'm curious to go there just to see why hydrogen does that.
The trihydrogen cation is formed, it's one of the most prominent, most common elements or atoms in the interstellar universe. And since Jupiter has lots and lots of hydrogen in its atmosphere, I'm talking about molecular hydrogen, H2, in its atmosphere. It interacts with cosmic rays, or I think in the case of Jupiter, with high energy particles trapped in the magnetic field causing the auroras.
I see. Cool.
Okay. So our next story is an update on the status of NASA's Psyche spacecraft, which is currently en route to the asteroid, believe it or not, Psyche. Its mission there will be to map the surface of the minor planet and establish the composition of its surface. And as with all important NASA spacecraft, redundancy is built into various systems on board, and that redundancy has apparently saved this mission. The Psyche spacecraft uses solar power to ionize and accelerate xenon atoms, expelling them from a nozzle to form an electric propulsion system. One xenon tank lost its pressure, resulting in the loss of propulsion, which would have been a mission-ending problem. But the backup propellant line has been activated to restore that lost capability. And this switch has now allowed the mission to proceed as planned and will be arriving at Psyche in August of 2029.
Cool.
And again, there's a link. So next.
Can anybody make the sound of that when the newspapers are rotating? What's the music from the?
I can't. So the next story is a cosmic collision has been thrown into doubt. Prior studies had suggested that the Andromeda Galaxy and our own Milky Way would collide in about 5 billion years, billion with a B. And this collision would radically disrupt both galaxies and eventually lead to a merger of the two systems. Newly analyzed Gaia data and Hubble Space Telescope data that consists of positions and proper motion observations have cast some doubt on this prior work. The new analysis has added in the effects of the Triangulum galaxy M33 and the Large Magellanic Cloud to models of the orbits. And Monte Carlo simulations of future paths suggest that a close collision is only likely at about a 50% chance. So in the diagrams on the right, there's 4 panels. The x-axis on each panel is an x coordinate centered on the Milky Way. The y-axis each panel is either the z direction in their coordinate system in the top 2 panels, or the y direction in the bottom 2 panels. The left-hand pair of panels are models or simulations including only the Milky Way and M31, and the right-hand panels add in M33 and the Large Magellanic Cloud. If you look at the lower left panel, you can see that it's basically just a horizontal line, and that's because you're looking at the Milky Way and M31 orbital plane, and with nothing else in the universe, they will be in a plane always. And so that's what's shown in that lower left panel. So the upper left panel is basically looking down on that lower left panel, and you can see that there is actual motion between the objects. So let me see where I am here. So the most dramatic differences between the panels are in the two lower panels, where the dispersion in the y coordinate in on the lower right-hand corner is much greater than the lower left-hand corner, which is the same plot, just it now includes M33 and Large Magellanic Cloud. This shows that that M33 and Large Magellanic Cloud produce some motion out of the orbital plane if Milky Way and M31 were the only things in the universe, and adding in that additional effect lowers the probability of an actual collision. And again, there's a link to the Nature article that you can go to.
I don't know if I speak for anybody else, but I'm extremely relieved.
Yeah, I've been losing sleep over this. So next.
I'm your straight man today, Wayne.
Yep. The largest observing program in the James Webb Space Telescope's first cycle of observations has released its first data set to the public. The Cosmos Webb project used the NIRCam instrument to perform a multicolor survey of 0.54 square degrees, which is, believe it or not, nearly 3 times the area of the full moon, and an overlapping 0.2 square degree area using the MIRI instrument at much longer wavelengths. The data set contains data from more than 10,000 separate images representing more than 250 hours of total exposure time, and can be used to study galaxy evolution over the history of the universe. The data release includes photometry, brightness information, morphological information, such as whether it's an elliptical galaxy or a spiral galaxy, that kind of stuff, redshifts, and a variety of physical parameters for more than 700,000 galaxies, remember, contained in this 0.54 square degree area. The release also includes an interactive data viewer to inspect the data in the catalog, and the image at the right is a screenshot that I took after zooming in to a small area of the data set using the interactive viewer.
Wow. Awesome.
It's a beautiful thing. That lower link at the bottom is the interactive viewer, and I highly recommend going and exploring it. Probably if you just do a search on Cosmos Web, 2025, you'll probably find it.
Cool.
And finally, our last story is not space related, but I thought it was pretty cool anyway, except circumstances that generated it. We have the first known video of the rupture of the Earth's surface during a major earthquake. On March 28th, 2025, a terrible magnitude 7.7 earthquake struck central Myanmar, also known as Burma, or used to be known as Burma, and it caused extensive damage, over 5,500 fatalities, and 11,000 injuries. So it was obviously a terrible earthquake. The rupture zone extended for 300 miles or 530 kilometers through central Myanmar, with the epicenter located about 6.2 miles or 10 kilometers underground near the city of Mandalay. It's hard to read on that map, but it's the black star toward the top of that red area. The video itself was obtained from a security camera near Tazi, Myanmar, which is south of Mandalay. And 2 links here will point you to the information, and if you go next, we'll get to the video, I certainly hope. So if you press play, so watch the light pole that's visible just above the fence, and when the shaking starts, you'll be able to see how far the Earth moved during the earthquake.
Wow.
Okay. So this is the first known video of a movement, at least of this magnitude or of anything of the sort. And want to play it again. And if you look to the upper left, there's a metal building. And what you can't see behind that metal building is, go ahead and play it, is there's a water tower. And during the earthquake, the water tower collapses and crashes to the ground. So in the upper left, and here comes the water tower.
Oh,
okay, you can kind of stop it. This all happens almost simultaneously. I think the water tower falls at 12 seconds in, and the light pole motion starts at 14 seconds. So if we could play it one more time, there's one more very interesting thing happening. Up in the upper right, there's a power electrical transmission power line tower. Watch it as the earthquake happens. So here comes the shaking.
wow.
And the tower collapses. So this was as I said before, a terrible earthquake. Many people died and were injured and much damage was done. But the science part of it was rather interesting. So that ends this month's What's Up in Space news headlines. Thank you for watching.
All right, thanks, Jim and Wayne. I appreciate it. Okay, so we'll move on to our members' Astro-Images. And I noticed that we have one person in the room.
The strawberry moon. It's one image was the one image, the left one. That one was when it was more above the horizon, but the middle one was like much lower. The lower it was, the more darker red it was. And that picture is me with my sea star and my iPad. I took the image on my iPad. And that top image, the red circle, that's the moon when it was near the horizon.
Wow, very nice. And the very red is, do you know why it gets more and more red like that?
This particular one, it was caused by something called a lunar standstill. So it's only you can only see it when it's low in the horizon. So you can only see it every 18.6 years.
Wow. Okay. Very cool. And I think also some of that is just like a sunset, just the way the atmosphere attenuates the colors.
That bright.
It wasn't that bright.
Yeah.
Okay.
Basically, all the blue light gets scattered out of your line of sight, so it gets very red. That's why we have a blue sky in the daytime.
Right. Okay. Well, great. Thank you for sharing those. Those are excellent. And Gary's in the room.
Oh, yeah. So at the end of an imaging session at Alpha Ridge, I think it was a maybe impromptu star party, I was breaking down my SCT and I had my origin next to me. So I typically hadn't been interested in globular clusters. I thought they were boring, but I decided I was going to just take a few pictures of some to see what I could get. So I spent 130 seconds on M13. And I don't know, maybe it's because it was such a short exposure and I didn't sort of blow it out. I could actually get the propeller. If you see, there's like a Y shape in the middle of the cluster. It's a sort of a defining feature of M13. So I was pretty happy with the image to be able to get that detail with just 130 seconds of.
Oh, yeah, I see what you're saying. I don't think I've ever noticed that. The Y there, the dark Y. It's cool. This was, you said one image?
No, it was 13 10-second images.
Okay, so 130 seconds.
Yeah.
So now I don't know the field of view, but I'm noticing I don't see the galaxy that
No,
Marcel
this
showed
is
earlier.
this is cropped pretty
Okay.
heavily.
Okay.
That's not bad for a day set. That's pretty good.
And then so the same night I moved over to M3. This was about 50 seconds, I think. It was a little bit less than a minute. Just again, you know, right out of the scope, cropped, and I thought it was fun to take a quick picture of it.
I think you said it, but if you didn't catch it online, this is with an Origin Smart Scope.
Yep.
So it's doing all the processing inside and all that for you.
Yep.
And that thing on the right is a foreground star.
Yep.
I forget what bright star that is, but.
How big is that Origin? I don't know nothing about it.
It's a 6-inch F2.
F2?
Yep. And this is the same night as I was tearing down my SCT spent. This was actually about 6 minutes. So it's the image is a little bit blown out. I think shorter time on these globular clusters is probably better. But anyway, it was just a fun 10 minutes, got 3 globular clusters that I hadn't been particularly interested in before. And now I think I'll go back and maybe see if I can get some better images out of them in the future.
Well, it depends on how you process them, because last month, Dale sent an image of M5, and it was something like,
it did not look like this.
It was like 40 hours, but it's you know, depending on how you process, you can clean up.
Yeah, I mean, I think the C star is the same way with Origin. You can collect the raw images and process them offline.
Yeah.
This was just letting the telescope use its own processing engine.
Okay, thanks for sharing those. Daniel, are you on? I thought I saw you online.
This was taken back in October. The one on the left was taken it outside my parents' house. See if you look above the trees, that was the that showed in October.
It's right.
And then on the side here was the night before was taken in Colombia. So above the trees is the comet.
Right,
and then right there is where the
arrow
arrow
is. Is it showing up on the screen?
Yes.
I think so. It's like
I can see it.
How's it look?
Right below center.
How's it look?
Yeah, it's kind of, maybe I should turn the lights all the way off. I think it's right here.
Yeah, I think so.
Yeah. And the other one's up above the tree. Yeah, we could see it, Daniel. And how did you do that? With your phone?
I put my cell phone on night mode, dusk, and a few second exposure, and the comet turned out well, I thought.
Yeah, great. Thanks for sharing those. We got a lot of talk about comets tonight. And Ken.
This is Sirius, and Sirius is a double star. It has a white dwarf that orbits every 50 years. And this year it said it's farthest from the star. So you can see I processed it in 2 different ways. The first way is really bright, and then the center I took it down and you can see the second star, the white dwarf, just below it.
Just a little tiny thing right there?
Yes.
So what am I, is this some kind of a mask or something? What am I?
No, I faked it. I processed it 2 different ways. The bright way is like a deep sky object.
I see.
And then the second way I didn't do any brightening of it at all. In fact, I processed it with the same way I process planetary images for the most contrast. So if I just showed that one image, you wouldn't see any of the background.
I see.
And I just cut and pasted this one point where it would belong.
That's cool.
And it should be interesting over the next few years. If I do the same thing, you should see it orbit to the left relative to those background stars. So that's the plan. As it gets closer, it should rotate to the orbit to the left.
So it's orbiting clockwise?
I'm pretty sure.
Okay.
In this view, it's
Oh, okay,
orbiting
yeah.
clockwise.
And
So
then,
are we looking down and it actually is going in a circle around the primary star?
Right, it's in an elliptical
Oh, okay.
ellipse,
But the-
and in 25 years, it'll be so close that nothing will be able to see it.
Okay.
I've been imaging it for about 5 or 6 years, and 6 years ago, I couldn't see it, and then it popped up one year, and then so over the.
cool.
But unfortunately, those images, I don't have any background stars, so I can't show you the orbit.
I see. That is so cool. So, all right, we're gonna monitor that over the next 15 years. We're gonna check in. Very cool, very cool.
This is my ugly image. Venus, its surface glows. It's so hot, it glows in infrared light. And if you image it at 1,000 nanometers or a micrometer, ironically, the atmosphere is pretty transparent in that wavelength. So this is the first time I've tried it. I just got the filter a few days before I took this image. If you look at the center one, you can kind of see the rest of the circle.
Yeah. Like those features are similar to these?
And so the Win-Chu-Post graphic is showing what the surface should look like then.
Oh, wow.
And they kind of match up. But in any event, you can definitely see the circle. So that's definitely the surface of Venus shining through the cloud layers.
Nice.
Cool. And some people online, I've noticed, they take them at different nights and you can see it rotating slowly because Venus rotates like at 243 days. So over the night, you can see it slowly rotate.
Oh, cool. I have not seen this. That's the first one I've seen.
This is my first try at it. Hopefully I'll get better at it.
I also didn't realize the regular ZWO would have much sensitivity all that far away.
I know it's kind of down the end, but it still obviously shows it.
Neat. Well, that's really cool.
And unfortunately, the 2600, that little glass thing in front of it is an infrared filter, kind of like cameras. So I have to use the 1600.
Neat. Okay. And get more CAD.
Sorry. I just took this of the vacuum cleaner galaxy at one of the impromptu star parties. People were looking at it, so I wanted to show people. It was a bad night. The seeing was terrible. The transparency was average at best.
But you got it. That's with your big mead.
Yeah,
yeah.
It's there. You can see. I think it's a different. You can see the hard spiral.
Oh, the bar. Yeah, sure, for sure. Okay, and then.
And this is the sombrero. It's a wider field. It's with a different telescope, 150 millimeter. And I liked it because the little star cluster at the upper right, you can see kind of different colors in those stars.
Yeah, that's neat. Yeah, you don't normally see a wide field on this sombrero.
Yeah, you see it.
Yeah.
So it's like going on around it.
Where was this take? Oh, from Alpha Ridge.
The same night.
Okay, so it's low on the horizon there. Interesting. Well, those are really cool. Thanks for sharing all four of those, four very different things. And thank you for everybody who submitted. Thank you, Harini, for submitting, and for those online, Daniel, thank you. So that's all we had for tonight. I appreciate everybody coming out to the room and for being available online. I'm going to stop the recording and maybe we can set up. We got a few minutes to kibitz here if anybody wants to just catch up and talk and ask any more questions of Marcel. So thank you. Anybody online have anything they want to end with? Okay, I'm gonna stop the recording.